Hi everyone, good evening. So in today's session, we're looking at the topic of circle theorem. Now, basically, when it comes to circle theorem, it's several rules that we have to remember in order that anything they give us, we are able to pull out what rule may be applicable to help us find that missing angle or that missing that missing angle. So it's basically where you have to be able to explain why certain angles are that specific value, and you must have backup for it. All right, so let's begin with our circle theorem. So basically, these are all of the rules we're going to learn. So I'm going to put it on the board on the screen, explain them, and you have to revise them for me. You have to know them by heart. All right, so let's take a look at the first one. Now it's in no particular order, right? So you cannot learn them as according to Theorem 1 or according to Theorem 6. The order in which I might teach it, another teacher might teach it in a different order, right? So my Theorem 1 might not be the same as your teacher's one. So because that is the case, we cannot learn it as by number. So Theorem 1, Theorem 2. We actually have to be able to explain it. All right, so let's make sure we understand the parts of the circle, right? Because they may ask you questions and they may give you information based on a circle on things that they expect us to know. All right, so first things first, this outer boundary of your circle, the distance around or the boundaries of the circle is known as your circumference. Right, so we know that the distance around is known as the circumference. On a side note, in order to find the circumference, we know the formula is 2 pi r, or you could know it as pi d, where 2 times r is your diameter. Right, so that's like if they ask you to calculate as a side. We know that the distance from the center to any point on the circumference would be your radius, right? So anywhere from the center to any point would be your radius. So of course, if you have a radius here and you have another line coming here, you know that that is also the radius once it's coming from the center. So just some facts that we have to be mindful of. So that means that this line would be the same as this line because this is the radius and this is the radius. So they are both the same length. Normally, in triangles and different shapes, they use these symbols, either double or a single line on each to show that they are equal or they are the same. Right? So we know that's the radius. If it is that you have a line going through the center and connect 2 points of the circumference, that's your diameter. It's important to note that the diameter is made up of 2 radii, right? That's the plural of radius. So if you have one radius on this side and another radius on this side coming together, the 2 of them will be your diameter. All right, so looking at all of the parts, if they give you a line that is not going through the center, right? So anytime there's a line that is not going through the center, let's say C is the center, you might also see it as O, or they'll tell you what is the center. If the line is not going through the center, but it's connecting 2 points on the circumference, the name of that line is called a chord. And your chord divides your circle into 2 parts, which is known as a segment, right? So this will be a segment, and this in green is also a segment. So your line, which is the chord, divides your circle into segments. So the smaller one, we call it the minor segment, and the bigger one, we call it the major segment. Right? So segments are very important when it comes to circle theorem. All right. So our next thing is that of the sector. Now, basically a sector is like, think of a slice of pizza. Everybody loves pizza. So basically, your sector is like a slice of pizza. It has 2 radii, right? So you have a radius on this side, a radius on this side. And it's bound by a part of the circumference, right? So this part of the circumference has a special name. And that special name, so this here, which is a piece of your circumference, is known as the arc length. So a sector is made up of an arc length and 2 radii, right? So this piece here is a sector, right? Remember the difference between segment and sector. So think of a sector as your slice of pizza. Now, if I remove this slice, I also have a slice arm, a sector on the other end, because I have a radii on this side, sorry, a radius on this side and another radius on this side, bound by an arc length. So by definition, this side that I'm shaded in green is also a sector. So to distinguish them, we can name them the bigger part, the major sector, and the smaller slice, the minor sector. All right, so let's look at the theorem or the rules. So let's look at the first one. Remember, it's in no particular order. So this one, we are seeing that if this is my center, if let's say we have triangles, right? So I'm going to explain it in layman terms, meaning ordinary terms. So let's say this line here is going through the center, right? So specifically, it must go through the center. Let's say we have triangles sitting on the diameter, right? So this triangle sits on the diameter. So it could sit in various ways. It could sit in that direction. It could sit in this direction. Right? So if you look, all of them, even if it's in this direction, they're all sitting on the same diameter. So the theorem, I'll label it as theorem 1. Right? So I'm going to explain it in very simple terms so you can remember it. If a triangle sits on the diameter, which is the line going through the center, the angle at the circumference will be 90 degrees. Right? So that's a rule. Once you have a triangle sitting on the diameter, the angles at the circumference must be 90 degrees. So this will be 90 degrees, this will be 90 degrees, this is 90 degrees. That's the rule. So we have to remember the rules. That's one. Another theorem is that, let's say you have your circle, but this time you have some triangles which are not sitting on the diameter, but they're sitting on a chord. Remember, the chord could be in any direction, right? Don't be fooled with it. Your chord could be in any direction, but it's basically where it's going, connecting two sides of the circumference, but it's not going through the center. So let's say we have some triangles sitting on the same chord. So they're all sitting on this chord here. So it could go in several directions, right? So they could have more than one, but they're all sitting on the same chord. Right? You could have them of different colors. But once they're all sitting on the same chord, we could identify that they're all sitting on the same chord. Then the rule will be that the angles at the circumference will all be the same. Right? So let's say the angle up here is A. This will also be A. This will also be A. So that's the rule. So once you could identify that you have triangles sitting on the same chord, you know that all the angles that are at the circumference will be equal. Right? So this is our theorem 2. Remember, you cannot remember it as according to theorem 1 or according to theorem 2. You have to be able to explain it. So in easy squeezy, we can say, so another way we could explain this is for this one, angles. Another way to explain theorem 1 would be angles in a semicircle, right? It could hit your terms like that, right? Because half of a circle is known as a semicircle. So you could say angles in a semicircle. That's for the first one. For this one, if you notice, all of these angles are in the same segment, right? So, I mean, you explain it as in as easy terms as you can recall, right? So we can explain angles in the same segment. So angles in the same segment of a circle or in other words, you can say that they are sitting on the same chord, right? So this is the chord they're sitting on, all of them sitting on the same chord. Right? So we should be able to, if we see them, we should be able to identify them. All right, so let's take a look at this one. Now, anytime you have the radius, remember the radius could be in any direction from the center, touching any point on the circumference. A tangent is a line that touches a circle only once on the circumference. So the tangent could be in any direction. So any straight line which touches the circumference at one point is known as the tangent. If at any point the radius meets the tangent, right, it could be in any direction. Once the radius meets the tangent, at that point, it's going to meet it at a right angle. So that angle where the radius meets is going to meet the tangent. It's going to meet it at a right angle, or it's going to be perpendicular to the line, or it's going to meet it at 90 degrees, right? So tangent, any line touching circumference at one point. Right, so this theorem, let's name it Theorem 3. Right, remember, it's like rules. So you just have to remember it and be able to look out for them. So your Theorem 3 is going to be a tangent of a circle is perpendicular. This is what perpendicular means, meets at a 90 degree. To the radius of that circle at that point. Right, so basically, it could be any direction right? Don't be fooled if the change of the direction of it on you. You have to be able to recognize your rule. Let's go on to another one. So we know what a tangent is. What if you have two tangents and those two tangents are meeting at a particular point? Just I'm going to make this a little smaller. So you have a circle, and let's say you have two tangents, a line touching the circle, but it's meeting each other at a point, right? So the two tangents, so this here is a tangent. This here is another tangent. Right? But both of them, they're connecting at an external point. Now, if that's the case, remember, this point here is going to be perpendicular, right? This point here is also going to be perpendicular. Now, the distance, meaning the radius meeting to the tangent, right? Now, the distance from here to the point is going to be the same as the distance from here to the point. So that means this length will be the same as this length. So we can work on that theorem. We can call it Theorem 4. Right. So the lengths of two tangents from an external point, this is the external point. So the distance from that external point to the point of contact on a circle, which is this point, they will be equal. So this distance will be equal to this distance on this end. All right, so let's take a look at another theorem or another rule. So basically, anytime you have a chord, right, remember chord is any line that cuts your circle into segments, or it cuts your circle, but not in the center. So anytime you have a chord and the radius meeting or cutting that chord, right? That point, so if this is the center, this is a chord, right? So this line here is your chord. and it's cut by the radius. I'll put it as R. It's going to cut it at 90 degrees. Right, so it's going to cut it at 90 degrees. Now, right, so this is radius. All right, so this will be our theorem number 5. Right, so we have, I'll write it and then explain it. Nice. So basically, the line joining the center of the circle, so like a center here, to the midpoint of a chord, that's this line here, meets it at a right angle. Now, the thing is with this is that we can connect these two lines here. And what you'll recognize is that you have a right angle triangle. So if we have this, let's say we were asked to find a missing side or a missing angle or what have you, we can apply the rules of Pythagoras theorem, or in terms of the angles, you can apply the rules of trigonometry as it's a right angle triangle, right? So in a case like this, a right angle triangle, we could connect those two lines and we basically just apply the rules of Pythagoras' theorem. Or tricks, right? Some of you guys have trouble with Pythagoras theorem and trigonometry. So what I'll do is on the same recording, if we get through it, all the theorem early, I'll go over the triangle rules before we practice it, right? So you apply your rules of Pythagoras theorem or trigonometry as it's a right angle triangle. Next rule. So let's say you have a chord. You know a chord could be in any direction. So it's not specifically in this direction that I draw it, right? So if you have a chord and you have two triangles coming off of that chord. So let's say you have one going to the center of your circle, right? So one triangle sits on the chord and goes up to the center of the circle. And then another one is sitting on the same chord, but it's going to the circumference. Now remember, that could go in any direction, right? Once it's sitting on the same chord, right, it could go anywhere, any direction, anyway. But once they're sitting on the same chord, one going to the center and one going to the circumference, the rule is that the angle at the middle is always twice the size of the angle at the end. So if this is A, the angle of the middle will be twice this. So if this is A, this will be 2 times that. Right? So let's say they gave you this one. In order to find this angle here at the center, you just multiply this first one by 2. If they gave you this value and they ask you to find this one on the outskirts, you just divide this inner value here by 2 and you'll get the outer one. Right, so that's the rule. So we'll name that Theorem 6. Right, so the angle at center or at the center is twice or 2 times the size which subtends to the circumference. Right, so once they're sitting on the same chord, and even the way that I explain it in layman terms, if you remember it better that way, once you can explain clearly your reasoning. So once they're subtending or sitting on the same chord, where one goes to the center and the other goes up to your circumference, the angle at the center is always double or twice the size of the angle at the circumference. All right, so let's take a look at another set. So we have a circle, and we know the definition of a quadrilateral as any 4-sided figure, right? So we know a quadrilateral is a 4-sided figure. So basically, if you have any quadrilateral whereby you have 4 points, all the 4 corners touching your circle. So it could look like this. It could look like this. Right? So once it's a 4-sided figure, whereby all of the corners are touching your circumference, it is known as a cyclic quadrilateral. right? So this is known as a cyclic quadrilateral. So let's just define that quickly. So if all four corners of a quadrilateral touches the circumference, so all four corners of quadrilateral touches circumference of circle. We have a special name for it, a cyclic quadrilateral. If all four are not touching, it is not a cyclic quadrilateral. So like, let's say you have one like this, and you have something like this. This is not a cyclic quadrilateral, and it does not follow the rules that we're going to look at. It must be that all the corners are touching the circumference of the circle. So all four corners of quadrilateral touches circumference of circle. It is a cyclic quadrilateral. Right, so all four corners, once it touches, it is a cyclic quadrilateral. So let's look at the rule behind it. So this will be our theorem 7. So once you have a cyclic quadrilateral, the opposite angles, so let's say this one and this one, they're facing each other, so they're opposite. They are supplementary, which means that when we add them up, they must equal to 180 degrees. Right? On this side, these angles are also opposite to each other. So when I add them up, they must equal to 180 degrees. Right? So that's a rule. Once it is that the angles are facing each other, they are supplementary. Right? And you could use the words opposite angles of a cyclic quadrilateral are supplementary, meaning they must add up to 180 degrees. Similarly, if they give us another, and let's say you also have a cyclic quadrilateral in this case here. Now, sometimes these lines, they may extend externally, right? So basically, this angle here is going to be an exterior angle. Right, so let's just change the color so you'll see it better. So this angle is on the outskirts of the cyclic quadrilateral. So we can call this an exterior angle. Right, so basically, I'm going to write the theorem. This one is going to be theorem 8. Right, so this theorem states that if we have an external angle, so let's say this angle here, it's outside of the cyclic quadrilateral, this angle would be the same or equal to the angle that is opposite on the interior side. So you see how this angle is here? Inside on the opposite end will be up here. So this angle will be the same as this one up here. Right. So basically, these are all of the rules that we have to look out for when it comes to a circle. So it's like you have to make sure that you know your rules, and in any question that they give you, you have to be able to identify the rules and use the reasoning behind the rules in order to find your missing angles. Another thing that we also have to apply to these would be your rules of parallel lines and so on, right? So there are others that we have to remember, but it's going to be linked to other rules that you know, right? So let's just recap some of those rules with your parallel lines, right? So remember, if you have parallel lines, those are lines which run alongside each other, but they don't ever meet. Let's say you have a transverse line which cuts it. We have to make sure that we go over all of them. So I'll go over them quickly. One, you have to know your corresponding angles, right? So remember your corresponding angles. I'll write it on the board. Right, so these are related to your parallel lines. Your corresponding angles is basically, let's say you're looking at a particular angle. If I were to shift this parallel line down to meet this one, so it's like I'm going to just drop this one to down here. This angle and this angle, they would be in the same position, right? So it's like they are in corresponding position. Corresponding angles are equal. Let's say on this side, if I were to drop this down, this angle and this angle, they are in the same position. So they too are corresponding angles. So they'll be the same size. So if this is 50, this is also 50 because they are corresponding angles, right? So you have to be able to note the reasoning behind it. If, let's say this one is corresponding with this one, so those two angles will be the same. And then finally, this one corresponds with this one. So corresponding angles is basically if I were to shift one of the parallel lines to meet the other, the angles will fall in the same position. So we call them corresponding angles and they are equal. Right, so you could remember to pause and screenshot when needed. I'm going on to the other. All right, so another rule regarding your parallel lines would be that of alternate angles, right? So alternate angles basically occur between your parallel lines. So basically, once you can identify a Z in any direction, so it could be that way, it could be this way. Once the sides of the Z are parallel to each other, right? It could also be in the shape of an N or an upside down N. So once you can see a C shape or an N or like a zigzag, but the ends are the parallel lines, those are known as alternate angles. So the angles in the arms of the Z or the N, right? So those angles within the Z shape or the zigzag shape or the N shape, those are known as alternate angles. Right? And basically alternate angles are equal. Right? So once you can make the shape of a Z on any direction, and if both sides are parallel to each other, they are alternate and they are equal to each other. I'm covering here. Make sure to screenshot as we go along. In fact, I'll just undo it. Right. So again, with parallel lines, if you look well, for parallel lines, you have straight lines. Right, so we have some parallel lines. So in this case, we have right, so in this case, if you look, we have a straight line, and angles on a straight line must add up to 180 degrees. Right, so in other words, they are supplementary. So if I have a straight line no matter how many times they're cut, once I add up all of them, they must add up to 180 degrees because it's a straight line. Right? So that's the reasoning. Let's say you have angles where you can see that there's an X in it. Right? So if you look here, I can see that I have the shape of an X. And that X could be sitting in any direction. If you have that angles in the opposite side of the X, if you look at it, it comes like you're facing it. It's right in front of it. So we call those vertically opposite angles. Right? So those are vertically opposite angles. And vertically opposite angles, once they're like facing each other, so those two will be vertically opposite. These two will also be vertically opposite. And vertically opposite angles are equal, so they'll be the same. So you have to be able to look at it and be like, okay, I can spot a vertically opposite angle. So if this is 80 degrees, this here will also be 80 degrees. Right? And you have to be able to give the reason behind it. All right, so let's take a look at another one with respect to this. So if we look at our parallel lines, you can look and see that in between your parallel lines, you can see that it forms like a half of a quadrilateral, right? So this here is a half of a quadrilateral where the sides are parallel, the parallel lines. I find, to be honest, it looks like a container, right? So your container could be sideways like this. Your container could be this direction. Your container could be in any direction. It could even be upside down. But once you have both sides of your container as the parallel lines, the angles inside of the container, right? So these angles inside of here, they are supplementary. And remember, supplementary means they must add up to 180 degrees, right? So these angles at the base of your container, no matter in what direction it may be, they are known as interior angles. Some books or some teachers may call it co-interior angles. So whichever one you use, it's perfectly fine. So if it is that they choose to call it co-interior, you use co-interior. If they just use interior, you use interior angles. So interior angles are supplementary. And what that means is that they must add up to 180 degrees. So if this is A and this is B, A plus B will be 180 degrees. All right, so these are all of the rules. There may be some others like rules of triangles and so on that we may have to apply. All right, so let's take a look at this question. So this question is coming from the January 2025 paper. Right, so this is a January 2025 paper. All right. So circle theorem, you could use in your or at the number 9. Right, so you could find it at number 9. Now, we went over all of the rules. Now it's basically you trying to be able to recognize those rules and use those rules in order to solve it. All right, so let's take a look at this first part. It says the diagram below shows a circle with center O. So we're identifying that this is your center. Right there and then you're supposed to be able to recognize that this is your diameter. They said angles P, the P here, Q, L, and N, they are all lying on the circumference. All right, so if they're all lying on the circumference, just a little connection, we could connect all of those points and form a cyclic quadrilateral. All right, just saying, right? We don't have, I just linking information. They said that LN, so line LN, that's going to be this line here, L to N, and NQ are equal. They showed that because they gave you these two lines on it, right? So anytime they want to show equal lines, they'll either have a single line on each of them, or they may double line it like this to show that they're the same. Then they said that RM, here's RM, is the tangent to the circle. So remember, tangent touches your circle only once. And they told us that angle MLN, right? So some students, they mix up how, or they lose track on how to label their angles. So basically, if they give you it like this, the angle is usually at the letter in the middle, right? So it's like it starts from M, going towards L, and then up to N. So the angle is usually formed by the middle, right? So angle MLN, and they sometimes use this symbol to show angle MLN, right? So they either use the word angle or they could use this symbol. All right, so let's begin the question. So the first part is said, explain why angle X, right? So angle X is here, and angle NQL. So let's draw that out to see. So NQL. So we want to show that that angle here, remember the middle letter shows where the angle is located. So they want to know why are these two angles equal? So one time you have to check back what rule showed us that angles at the circumference are equal, because both of these are at the circumference. And if you look at it, they are both sitting on the same chord. Right? Because look at this one. If this is the chord, I have one here. And if it's the same chord, I have another one coming off of the same chord. So that's a rule. So we have to use that rule. So you're going to explain that now you want to label using the letters which they gave. Right? So you use the letters to explain or to name the lines and so on. So you could start by stating the rule. Right? So angles X, right? So angle X, if I had to name it, I'm just gonna name the lines, the points that surround it. So angle X is actually angle NPL, right? So that's just in case they didn't label it with a letter. So angle X and angle NQL, right? So they both are subtended by the same chord. They're both sitting on the same chord, right? So angles X and angle NQL both subtends or I can say are both subtended by the chord, right? So this is the chord here. So by the chord NL, right? If it is that you are not familiar with all of the various terms and it's not sticking, explain it in simplest terms. The angles P and Q, right? The angles at P and at Q, they are both forming triangles which sit on the chord NL. Angles which are standing on the same chord are equal, right? So angles sitting on the same chord and I don't know, I could say that it reaches to the circumference, or I could use the term they're in the same segment, right? Because they're in the same segment. So it depends on how you choose to explain it. So angles sitting on the same chord, right? And side of the circumference I'm going to use segments. They are equal. Right? So all they asked us was explain why they are equal. So in other words, they're testing your knowledge of the theorem. They're testing to know if you know your rules. Right? They didn't ask you what it was as yet, but they're asking, you know, what is that? All right. So pausing here for this one. All right. So for part 2, part A, they ask you to find out what is the value of x. Now, we have to look at it in terms of what angles we have surrounding it, right? We want to know what rules we could get from this. All right, so let's take a look at this part. All right, so if we look here, remember I showed you guys there is a quadrilateral. Now a little suggestion, right? A little suggestion. Now for me, in order for me to like be able to see the rules, I have to draw up on that paper, right? So in order for me to be able to see and help me to focus, right? Because if I just look at the page, I'm just going to see black lines on a white paper, right? I don't know about you, but for me, if I just try to like look at it just like that, I don't really see it. So I actually have to like, you see how I drew it out for you to see? I actually have to draw it out for myself to see. So I have a little suggestion. One, do not draw on it in permanent ink. Right? The reason why is because once you draw on it, it's kind of hard to unsee it when you don't want to focus on it. Because like once you draw, your mind focuses on what you drew over everything else. However, you can use your pencil to draw it, and then you just erase it to unsee what's like whatever you're finished with. Another suggestion is that, you know, those erasable pens, you know, that there are pens that you could erase. My suggestion is that you could use it and you just erase in case that you don't want to focus on a particular thing. So either use a pencil or one of those erasable pens. All right, so if we look at this here, we are seeing that this tangent is meeting this quadrilateral here. right? So it's actually meeting this quadrilateral here. Now, if you look at it, recall your rules. When we have quadrilaterals, we want to note what rules do we know, right? So we can look out for quadrilaterals, etc. Now watch me on this part, right? So we know that I want to unsee the quadrilateral, right? If you look here, you have a diameter and it's meeting the tangents, right? So unseeing the quadrilateral, as I kind of lost track as to where I was going with that quadrilateral. So I have a diameter meeting your tangent. You know, once the diameter or the radius meets it meets it at a right angle. Right, so it's going to meet it at a right angle. So watch this. If this corner here must be 90 degrees, and they told us that this part is 63, then this missing part inside, we could find out what that is. Right, so we could find out what is this angle here, because that will be 90 minus 63. Right, so you do your little working, you show your little working, right? So any space provided, you do your little working, just as a guide as to where you're going. So that's 90 minus 63. Remember, we could use our calculator for paper too. So 90 take away 63, I got 27. So this part here is 27 degrees. Right, so this angle that I colored in here is 27 degrees. Now, coming back to here, remember this is my diameter. I'm going to outline it in blue. So this is my diameter here. And if you look, there's a triangle on that, coming off of that. That includes that 27 degrees. You see it? Now, any angle that is in a semicircle or in the half of a circle or any triangle which subtends to the circumference from the diameter, the angle at the top is 90 degrees. So this angle here is 90 degrees. That's not y, yeah? That's y, and the extra piece there must be 90 degrees. So if you look at it, you could recognize that we have a triangle. Angles of a triangle must add up to 180 degrees, right? So you could do all of your work, and remember, you have to show all of your working, right? So what I do is I do all of my working to ensure that it's legit, and then I'll write my reason to support it, right? So I add up what I know, so that will be 90 plus 27, right? So that's 9, 10, 11, 117. And then I subtract it from the 180. Right? Because remember, all of these angles, 1, 2, 3, must add up to 180. So I add up the two that I know for sure, and I subtract it from 180. I'm using my calculator. 180 minus 117, and I got 63. So that means this missing angle here, x, is 63 degrees. So I know I'm comfortable with my reason, my working. So I'm gonna explain it in very layman terms in order to help us to explain. So you'll say that the line, use the lines in order to help you explain it. So this line here, which is your diameter. So the diameter, my only problem is I've covered this letter here, and I can't remember what letter it was. P. Right. So we can explain that PL, the diameter, meets tangents MR at 90 degrees, right? So we know that this here has to be 90 degrees. So we explain that angle PLN, so angle PLN, remember the letter at which the angle is at, so this angle here, let me shade it over in green to make sure we see it. So this angle here is at L, so you want to show that at the middle, right? So that has to be at the middle of the point. So PLN, so angle PLN is 27 degrees, right? It's already showed you working, right? If you want, you could show it again. 90 minus 63 equals 27 degrees, right? Remember, it's math, so you try to use it doesn't have to be a lot of words. Show your work and explain it clearly, right? So next, we know that triangle, right? So I'm going to use the symbol, triangle NP, right? So remember, this is NPL, sits on diameter, right? So I'm using simple reasoning, sits on diameter. So angle at N equals 90 degrees, right? We know that triangles add up to 180. Therefore, 180 minus, you show that you add the two sides that you know, 90 plus 27, that's 117, is equal to 63 degrees. So x is 63. All right, so let's take a look at y now. Right, so make sure you guys have it. So we know that x is 63, and we gave the reason behind it. So the next step, they asked us to find y. Now, if you look at y is a part of the 90 degrees here. Now, let's take a look at this. So I'm going to use the colors, but I'm using blue this time. So if you look at y is actually in between is an isosceles triangle, right? So it's in between an isosceles triangle. And with respect to this, let's just recap those triangles to make sure that we remember. Remember, there are different types of triangles. We have 4 main types. We have a right angle triangle, where one angle is 90 degrees. You have an equilateral triangle. Equilateral triangle, all sides are equal, and hence all of the angles are equal. So if all the angles must add up to 180, then 180 divided by 3 will give me 60 degrees. So each of these in an equilateral triangle must be 60 degrees. Right? So that's the equilateral triangle. Right? So we have to make sure that we are familiar with all of the properties. Then you have your isosceles triangle. So the isosceles triangle is where 2 sides are equal, and as a result, the angles at the bottom of those 2 sides will be equal. So if this side is equal to this side, the angles at its base will also be equal. So we're seeing something there. So that's an isosceles triangle. And then, of course, you have your scalene triangle, where none of the sides are equal. So watch this part. If this is an isosceles triangle, it means that this angle and this angle will be equal. Don't we know this angle? Remember, this was sitting on the same chord as this one. So this and this would have been the same. So if this is 63, here's also 63. So if I know that this is 63, this whole thing here is also 63. And y is the third angle in this triangle. So we could add up what we know and subtract it from 180. So once you're comfortable with your reasoning, right? So you go through it, so you make sure you're comfortable. You go on and try to explain it, right? So I recognize that angle NLQ. Use the letters. So triangle NLQ is an isosceles triangle. Right? So you use your terms. Right? So isosceles triangle. So triangle NLQ, we use the ends of it, the points, to name it, is an isosceles triangle. Is an isosceles triangle. Right? We know that angles, right? QLN, right? So the one that you're referring to, so I'm referring to this one here. So that letter, that point has to be at the middle. So angle QLN, right? So I named it this way. I mean, if you name it the next way, meaning N and then L and then Q, that's okay, right? Right? So if I'm referring to the angle, I'm looking at the one at the middle, right? So angle NLQ, that's this one here, is equal to angle NQL, right? So Q is at the middle this time. That's what we're referencing. So NQL, they are equal. Angle NQL, remember we already know that that's equal to X. And X is 63. Right? And because it's a triangle, so we add what we know and subtract from 180. Right? Depending on your time, we could have just showed that. Right? So instead of explaining it, we could have just showed the working if you don't have enough time. Right? So I ended up with this. Remember, use your calculator in your paper too, anywhere that you can to speed up the process. Right, so 63 by 2 minus 180, I got 54. Right, so make sure clearly you state y is equal to 54 degrees. Right, and that's it for this one.